So today's lecture is the third of our 12 lectures. We'll be talking about amplitude modulation. It's the first of 3 lectures where we'll be talking about amplitude modulation. Actually, the first of 4 lectures where we talk about amplitude modulation. That doesn't mean it's more important than any other modulation. It's just because it's the first, we take it slowly. But then we do 1 week on FM. 1 week on FM demodulation, and then very quickly we do all the pulse modulation and digital modulation. So just as a reminder, we introduced you to modulation last week. We did a problem class about that. We spoke about how modulation is changing some property of a high-frequency carrier so that a baseband message can be converted to a bandpass signal. We spoke about why we do it, but we didn't speak about how we do it. We spoke in very general terms about changing amplitude and changing frequency. But we didn't describe in detail how that is done, neither mathematically nor in terms of the electronics. So this is the tree diagram, the schematic, the array of different bandpass modulation schemes that we'll be looking at this semester. That's not all the modulation schemes, but these are the main categories. Analog and digital. Today we'll be talking about a type of analog modulation called amplitude modulation. Now, all these, 1, 2, 3, 4, all of these are called amplitude modulation. But for today, and just for today, only this, DSB-LC, is what we're going to call amplitude modulation. So amplitude modulation refers to all of this. But when you simply see the letters AM, if you see that on a radio, or if someone says we're using AM, or sometimes it's called full AM, when you see that, we're referring to DSB-LC, which we're going to cover today. Why is it called DSB-LC? Each of those letters will make sense, hopefully, by the end of today. So today we're going to be talking about amplitude modulation. Next week we'll be talking about different forms of amplitude modulation that are not called AM. So today we'll be talking about amplitude modulation. We'll introduce something called the modulation index, or the depth of modulation. We'll be talking about AM in the time domain and in the frequency domain. In the frequency domain, remember from last semester, a frequency domain representation is what we call a spectrum. So we'll be talking about a time domain signal and a frequency domain spectrum. I'm not sure if this mic is working. Can everybody hear me at the back? Okay, next week we'll talk about the opposite of modulation, which is demodulation. And every modulation scheme we'll look at, we'll talk about modulation and then demodulation. So one is the opposite of the other, but they're often very different. That's just a word cloud of the kind of things you'll come across. So you'll hear this word modulation, carrier, and sideband a lot. You'll hear spectrum a lot. But look at this word here, power. We'll be talking about power a lot. Not today, but we'll be talking about power a lot. It's really important. There's also this word here, envelope. We'll be talking about that a lot. So, AM, what do we mean by AM, amplitude modulation? It's the process of changing the amplitude of a carrier, which has a higher frequency, in proportion with the amplitude of a message. So the message is your baseband, your AM is your carrier. Why do we use it? As you saw in the video, it's used in commercial broadcasts. We also use it for two-way mobile radio. So amplitude modulation comes in different forms, different flavors. Today we're only looking at the first of these, DSB, LC, or AM, sometimes referred to as full AM. So today we'll be looking at full AM, the first of those. So DSB stands for double sideband, large carrier. If we don't have double sideband, we can have single sideband, or it's sometimes called suppressed sideband, but SSB, single sideband. We can also have double sideband without a carrier, DSB, SC, so double sideband without a carrier. And there's also something called vestigial sideband, where you have a little bit of one sideband and you have a full second sideband. So we're going to be talking about AM or full AM today. So, what's going on? I don't know why this isn't animated. It was animated in my PowerPoint. But anyway, basic amplitude modulation. What we do is we take a low frequency baseband signal, so the signal from this mic, for example. Okay, so the signal from this mic will be a low frequency baseband signal. What kind of frequency do you expect from a microphone? What kind of frequency range? Anyone? You need to have some idea of what frequency we're talking about. What frequency will a microphone produce? If I was talking into the microphone, like I am now, what kind of frequency am I generating? So the human ear only responds to up to 20 kilohertz, and that's if you're really young. You would be lucky if you heard anything above 16 kilohertz. I probably can't hear anything beyond 12 kilohertz. But my voice contains components probably no higher than 5 kilohertz. Okay, so our baseband signal, the signal from the microphone, we're talking about kilohertz, low kilohertz. For AM, we're talking about kilohertz. If it was music, it might be 10 or 15 kilohertz, but it's still kilohertz. It's not hundreds of kilohertz. It's all in the region from 1 kilohertz to 15 kilohertz. That's your baseband signal. Something's happening after the signal leaves the sensors, leaves the microphone. Something is happening, and it's being mixed somehow in this magic box called a modulator. It's being mixed with a high-frequency carrier. What kind of frequency are we talking about? What kind of frequency? If my voice, if the message is in kilohertz, your frequency for the carrier will be much higher than that. It'll be hundreds of kilohertz. 100 kilohertz, 200 kilohertz, 500 kilohertz, 1 megahertz, 10 megahertz, that kind of range, okay? We're not talking about 100 megahertz. 100 megahertz, that goes into FM territory, shorter wavelength. So something is happening with this high-frequency carrier and this low-frequency message, some kind of mixing that results in that signal there. Now that signal there, is it a high-frequency signal or a low-frequency signal? The signal on the right, the AM signal. Do you think it's high-frequency or low-frequency? It's clearly high-frequency. It has the same frequency as the carrier. But what's changed? The amplitude. And if you look at the amplitude, that, if you surf the top, that's called the envelope. So if you surf the envelope of the top of those carrier peaks, that's the signal. That's the low-frequency signal. So the low-frequency signal has been put on top of the carrier somehow. Today we'll be looking at that somehow and see mathematically what's going on. So, modulating signal, carrier, somehow they're mixed together, we produce the modulated signal. This is called a bandpass signal. So, this is bandpass, this is baseband, that's your carrier. This is really short, all right?
What is amplitude modulation, AM? When the amplitude of high-frequency carrier wave is changed in accordance with the intensity of the signal, the process is called the amplitude modulation. In the amplitude modulation, only the amplitude of the carrier wave is changed. The frequency and the phase of the carrier wave remains constant. The first visual shows the principle of amplitude modulation. The diagram also shows the audio electrical signal of frequency Fs. The second visual shows a carrier wave of constant amplitude with frequency Fc. The third visual is the amplitude modulated wave. It is to be noted that the amplitudes of both positive and negative half cycles of the carrier wave are changed in accordance with the signal. Thus, the amplitude of the modulated wave possesses the frequency of the audio signal waves.
That was it. So that was just an animated version of what we've been saying. We've got low frequency message, high frequency carrier, they're mixed together. You're probably fed up of me saying that already, but I'm going to keep saying it because it's really important. That's what today's lecture is all about. It's about how we take a low frequency signal from a sensor like a microphone, and then we mix it with a high frequency carrier. So now we're going to express it mathematically. So I'm not going to use my voice, I'm going to use the simplest message in the world, which is simply a sine wave. So the message is no longer a voice signal, it's now cosine omega mt. The amplitude of the message is A subscript m, not to be confused with AM. Okay, so we've got a message that looks like a cosine. I know that doesn't really look too cosinusoidal, but imagine that to be a cosine, okay? So AM cosine omega mt. Omega m is low frequency. Omega m is 2 pi times something like 5,000. That's your message. Let's call it m of t. It's a signal, a function of time. That's why we have brackets t. The carrier, also a function of time. It has a separate amplitude, AC, separate frequency, omega c. Omega c is much higher than omega m. Not twice, not 3 times, but something like 10 times, 20 times. Okay, and what we're producing is this bandpass signal, S of t. So what do you think is happening between M of t and C of t? Are they being multiplied? Are they being added? Is it an integration? Is it a convolution? What kind of operation is combining these? What do you think happens inside the modulator? Take a second, share that thought with the class. What do you think is happening inside the modulator? Remember, we said today's lecture is all about this somehow. What is happening inside the modulator? How are we generating AM? So before we actually talk about it, tell me what you think is happening. Now, multiplication happens in a different type of amplitude modulation called DSB-SC, double sideband suppressed carrier. Okay? That's where there's just a simple multiplier. But in AM, it's a little bit more than that. Because if you multiply a sine wave times another cosine wave, you don't get that shape that we were looking at. So if you look at the shape we were talking about, this sine wave that changes amplitude, it's not enough just to multiply the two. There's a little bit more happening. Yeah, modulation index does come into it, yeah. There is multiplication. The reason I'm asking you to think about it is so that when you look at the answer, which is really easy, you appreciate it a little bit more. So yes, there is multiplication happening, but it's not just multiplication. If you multiply two cosines, you don't get that. Is it a convolution? It actually isn't. Let me think. It's a convolution in the frequency domain, yeah? Because there's multiplication in the time domain, it is a convolution in the frequency domain. So yeah, I'll allow that. But it's not convolution in time, no. It's not like system impulse response and convolution, no. Okay, so you all carrier plus carrier times baseband times index. Well done. So somebody's looked at the next slide. So this is what happens mathematically. So this, if you like, is the beginning and the end of today's lecture. If you understand this, there's nothing more to say today. This is what is happening inside the modulator. Everything else we talk about today is just reinforcing this. So what have we got here? We've got the red signal, low frequency, baseband signal. Remember we said AM cosine omega mt? Now I've simply written it as 2 pi fmt, same. And the carrier AC cosine omega ct, I've simply written it as 2 pi fct, same thing. Now, the green and the red are being multiplied. So everybody who said multiplication, you're right. There is multiplication going on. But we're also doing two things. We're scaling it. So we take the red signal and we scale it. We multiply it by a constant. And we clamp it. Clamping is adding DC. It's like shifting it upwards. So imagine that red signal being shifted upwards. That's called a DC shift or a clamp. And after adding that constant, 1, we then multiply it by the green signal. So you shift it and then multiply it. That way, we have this envelope that doesn't equal to 0. The envelope is always positive. All right, so this is mathematically what happens inside an AM modulator. So, remember we said 3 things we're going to mention today. AM modulation, modulation index, and spectrum of AM. This is the second of those 3 things, modulation index. Modulation index describes how deeply we have modulated. How much have we modulated this? So we have a carrier. Imagine that carrier without any change in its amplitude, just a constant carrier. There's no message. And if I start impressing the message upon the carrier's amplitude starts changing. And I can keep increasing the depth of modulation until the amplitude has a significant variation. That's called the depth of modulation, and that's your modulation index. It's the product of m times Ka. What we're trying to do is encode the message in this envelope. And we don't want this envelope to ever equal to 0. If this envelope is ever equal to or less than 0, we lose the signal. We'll talk about that in more detail next week. So our modulation index, our depth of modulation, can be 0, and that means we've not modulated at all. We're just sending a carrier, useless. And it can be anything from 0 to 1, or from 0% to 100%. 100% is where it's fully modulated, where the envelope at some point equals to 0, but is not less than 0. What's going on? Okay, so this is just repetition. Now, looking at your modulated signal, your bandpass signal, your AM signal, you have a highest point, that's the maximum amplitude, and you have a lowest point, the minimum amplitude. The depth of modulation, the modulation index, is related to the difference of those two numbers. So if you take the difference of those two numbers, divided by the sum of those two numbers, that gives us the modulation index. There. So the modulation index is the difference of the maximum amplitude minus the minimum amplitude divided by the sum of the maximum amplitude plus the minimum amplitude. So that's your difference, A, and that's your sum, B. You divide the two, that gives you your modulation index. I don't know why the visual isn't showing. Can you see the signal when you look at it? Yeah. Can you show me what do you see? You see it. Okay. That's puzzling. That happened last week as well. So, can you calculate the modulation index from that signal that you're given? I haven't given you the frequency, but you know the amplitude. So from the amplitudes, can you calculate the modulation index? Okay, well done. That's the correct answer. I can't see the signal on my screen, so I can't comment, but it's the maximum amplitude minus the minimum amplitude divided by the maximum plus the minimum. So there's something called overmodulation. That's where the modulation index is bigger than 1. It's greater than 100%. That's where the minimum amplitude, so you've got A max and A min. Your minimum amplitude is 0. So you have these 0 crossings. So if you look at the envelope, there, it's still okay, isn't it? It still looks like my message. But the phase has changed. We have a 180-degree change in phase. So it's not okay. That's a form of distortion. So when the phase changes, that's a form of distortion. So what we have is a distorted signal. We don't want that. We call that overmodulation. Overmodulation isn't good. It's not like oversampling, which is good. Overmodulation isn't good. Okay, there's no such thing as undermodulation, but there's overmodulation. Overmodulation is what we're looking at here. It isn't good. It's a form of distortion. So, spectrum. Remember we said 3 things? Amplitude modulation, modulation index, spectrum of AM. This is the final thing we're going to talk about. The spectrum is how does that signal, how does this look in the frequency domain? So, let's look at it mathematically. What we're doing is 2 things. We're adding DC and then we're multiplying. What are we doing inside an AM modulator? We're adding DC, scaling a little bit, then multiplying. So the 2 operations which will reflect themselves in the frequency domain, which will change the shape of the spectrum, are adding DC, or add a DC component, and then multiplying. What does multiplication do to a spectrum? If I take a signal, I multiply it by a cosine, what does that do to the spectrum? If you remember, from week 6, week 5, last semester, properties of the Fourier transform, there was something called the frequency shift property. And I called it the modulation property. And you said, why is it called modulation property? And I said, I'll answer that next semester. So the modulation property is a frequency shift property. When you multiply something by a cosine, the spectrum is shifted. It's shifted up by that frequency, by the frequency of that cosine. That's why it's called the frequency shift property. But frequency shifting is what modulation is all about. Modulation is a frequency shift. So when we take our signal, let's say it was that cosine omega m. If I were to add a DC, so if this is my message, that's what the spectrum looks like, FM, or omega m. If I add DC, that's my DC. And then I shift that, so you need to remember there's also one at minus FM. If I were then to shift that over here, this is my bandpass spectrum. So the DC, harmless DC, 0 hertz, has now become FC, a carrier term. My voice or my signal, my sine wave, 5,000 hertz, has now become FC plus FM. So we have an FC plus FM. We have 100 kilohertz plus 5 kilohertz, 105 kilohertz. That's your omega C plus omega m. And then we have the other one, omega C minus omega m. That's why we call it double sideband, because we have an upper sideband here and a lower sideband here, omega C minus omega m. So that's the spectrum of my AM signal. Now, if my signal isn't a sine wave, if my signal has an arbitrary spectrum, a continuous spectrum that looks like that, for example, it could look like anything. It could look any shape you like, but I've just drawn an arbitrary spectrum, band limited to FM hertz. So what's the bandwidth of my signal? FM, because we take from 0 all the way to the highest frequency component. That's my baseband message. After modulation, just like this, it gets shifted up all the way to FC. Now, FC isn't that close to FM, so I've exaggerated. But to squeeze it onto the slide, I've had to compress the frequency axis, so hence you have that crumpling there. So FC is your carrier frequency. The carrier component, that's the DC term that we added. So that's my upper sideband, that's my lower sideband, and the total bandwidth is now twice FM. So if FM was 5 kilohertz, now the bandwidth is 10 kilohertz. So why do we call AM DSB LC? Because DSB stands for double sideband. There are 2 sidebands, upper and lower. Don't confuse this with the upper sideband and this with the lower sideband. No, the negative frequency is not called the lower sideband. This is the upper sideband. This is the lower sideband. That's the image of the upper sideband. That's the image of the lower sideband. But this is upper, this is lower, this is the carrier component, and that's the bandwidth. Okay? This is incredibly important, incredibly easy. There was a question about it last year. I think it was last year. We didn't have this slide last year, and many people got this question wrong. Now you have this slide, no excuses. So, a signal that looks like that, the shape of the spectrum hasn't changed at all. The only thing I've done is I've added this negative part. And if you notice, it's a reflection. So some people in the exam, what they did is they took the positive sideband and they repeated it here, but they didn't reflect it. So I've tried to make it look clear enough so that one is a reflection of the other. So the upper sideband is a reflection of the lower sideband. Okay? So the total bandwidth doubles. That's why we call it DSB. Where did the LC come from? DSB LC means double sideband with a large carrier. This is the large carrier component. Why is it large? Well, it looks large, doesn't it? It looks bigger than the sidebands. It's a large carrier component. Why is that important? We'll talk about that next lecture. That's important for demodulation. Okay, so this is the spectrum of an AM signal where the signal isn't a pure sine wave. If it was a pure sine wave, the spectrum would look like that. Really simple, really boring. In practice, this is what your spectrum might look like. Okay, we basically finished. You might want to have a look at some of these little applets online. There are plenty more. I just chose these. Let me see if I can get this to work. So here we have the carrier in blue, high frequency, the message in red. And I can change the carrier frequency. And I can change the message frequency. See how that changes the AM signal. What do you think the modulation index is here? The modulation index here is how much? 100. It's 100%. This is full modulation because you've got these points here where you have zero amplitude. This is full modulation. I think you can change the depth of modulation. See, now 80%, 70%, 60%, 50%, 30%. I'm changing the modulation index. What's the modulation index now? 0. There is no modulation. I'm just transmitting the carrier. Can you hear how that changes? That's just a carrier. Sorry if it's annoying. There, maybe that's better. So that's your carrier. That's what it sounds like. You'll never hear this because it will obviously be in kilohertz. It'll be electromagnetic, it won't be acoustic. But this is just as a way for you to visualize it. So spend some time playing around with that until you get an idea of how it works. This is a nicer visual, except you need to download it onto your computer. Okay, I can't demonstrate it for you. But this is a nicer visual. Why? Because it shows you the frequency domain representation. It shows you how the carrier goes up and down. As you change the frequency of the carrier, how this moves to the left and to the right. And it shows you how FM, the sidebands, move to the left and to the right. I can't demonstrate this to you. I don't think, yeah. I don't think that's even working. But there, you see, as I change the depth of modulation, it should change the height of those two peaks. Yeah, it worked there. And if I change the frequency, it should move the carrier to the left and to the right. No, I'm changing the modulation frequency. So I'm moving the sidebands closer and further away from the carrier. So the sidebands are getting closer and further away. So I think that's the final thing, just for fun. What do you think I'm showing you here?